In this video, we're going to learn how to calculate the equilibrium constant K given the molar concentration of reactants and products at equilibrium. Let's look at the same graph of a chemical equilibrium reaction that we looked at in the previous video. I want to remind you that in this region in red is when the reaction has not reached equilibrium, and this region in green is when the reaction is at equilibrium. So the concentrations of reactants and products is going to be different before equilibrium happens and after equilibrium is reached. Take a look at how those numbers are slightly different. This is crucial to understanding because when we want to calculate the equilibrium constant, you calculate it as a ratio of the concentration of products and reactants present during equilibrium. That means we'll be using the concentration values that are present during equilibrium. So here is the formula. We have a general equation: 2A reacts with 1B to produce 3C and 2D. And this is an equilibrium equation. If this is the general equation, to calculate the equilibrium constant K, we'd need to put the products from the chemical equation on top of this equation. These are being multiplied. The reactants from the chemical equation, those go on the bottom of the equation, and those are also being multiplied. Notice that the coefficients from the chemical equation are written as exponents in the equation too. Don't forget this step. See how the 3 becomes the power of 3, and the 2 becomes to the power of 2. Same thing for the reactants on the bottom. The 2 becomes to the power of 2, and there's a 1 here. B is to the power of 1, but we can skip this step because it turns out it makes no difference in the end. So to calculate the equilibrium constant, it's basically the products multiplied together divided by the reactants multiplied together. And you add in the exponents from the chemical equation. Simple. Here's a few key ideas that I want you to be able to deduce from the equation. If you calculate the K value and it turns out that it's a lot bigger than 1, that means that during equilibrium, there's a lot more products because the numerator part of the equation, which was the products, must be bigger. If you calculated the K value and it's a lot smaller than 1, like a tiny decimal number, that means that during equilibrium, there's a lot more reactants than products because the denominator part of the equation, which was the reactants, must be bigger. If the denominator is big, then when you calculate K, K will be tiny. Lastly, if K is approximately 1, then that would mean that during equilibrium, the amount of products and reactants are about equal. This should make sense because the only way K would equal 1 is if the numerator and the denominator are the same. Here's the actual final note on this slide. You plug in concentration values into the equation if they are gases or aqueous. You actually don't plug in substances into the equation if they are solid substances or liquid substances. The quick explanation is because you can't have a concentration for a solid or a liquid. For example, a rock. A rock is solid, and you can't have a concentration for a rock. It doesn't make any sense. Another example is pure liquid water. Pure liquids don't have solute in them. And that means that if it doesn't have solute, you can't have a concentration of anything for a pure liquid either. And that's why you can't plug in solids or liquids in the equation. You only plug in gases or aqueous substances. Okay, I lied. The last thing is the brackets here. The brackets are a shortcut to say concentration. All right? Okay, that's really it. So let's get on to our examples for calculating equilibrium constant K. Here's our first example out of 2. Sulfur dioxide reacts with oxygen gas to produce sulfur trioxide, which you can see in the chemical equation below. At equilibrium, the concentrations of each gas was found to be 0.10 molar for sulfur dioxide, 0.30 molar for oxygen gas, and 0.45 molar for sulfur trioxide. Calculate the equilibrium constant K. Okay, so this is really easy. You just start by writing the equation for equilibrium constant. KEQ is equal to, and now remember that it's a ratio, so it looks like a fraction, and on the top of this fraction you have the products multiplied together. The product here is going to be sulfur trioxide. So we put the concentration of sulfur trioxide on the top, and you do write the coefficient of 2 since as a square to the power of 2 here. On the bottom, you're supposed to put your reactants. We have two reactants. The first reactant is going to be sulfur dioxide, and there is a coefficient of 2, so we're going to put to the power of 2 here. And this is being multiplied to the other reactant, which is oxygen gas. And since the oxygen gas does not have a coefficient, or it has a coefficient of 1, we don't have to write to the power of anything here. It's just going to be to the power of 1, which is nothing. Okay, so now we just plug in the numbers. As long as you know what the numbers are from the problem, you would be able to plug it in really easily. So for the top, for sulfur trioxide, the concentration is right there, 0.45. And I'm not going to actually write in the unit here. I usually always write in the units, but I'm going to tell you that the units pretty much always cancel out for these calculations to calculate the constant. So don't forget to square it because there is a square in our original equation. Now we're going to write down the numbers for sulfur dioxide. Sulfur dioxide was 0.10 molar. This one is also squared. And then we multiply it by the number for the concentration of oxygen gas, which was 0.30. Okay, and then you basically type this in a calculator. I'm going to kind of simplify this down on the calculator. We should get on the top, 0.45 square is going to be about 0.2025. And on the bottom, 0.10 square is going to be exactly 0.01. And then there's the 0.30. And now you type all of this in a calculator. If you're not sure how to type this in a calculator, you take 0.2025, divide it by 0.01, and then divide it by 0.30. So if you type all this in a calculator, you should get approximately, so I'm going to make a squiggly equal sign, which means approximately, 67.5. And since this number is bigger than 1, that means that this equilibrium favors the products a little bit more. Here's the second example. Nitrogen gas reacts with chlorine gas to produce nitrogen trichloride. You can see that in the chemical equation below. At equilibrium, the concentrations of each gas were found to be yada yada yada. So there's the equilibrium concentrations. Calculate the equilibrium constant KEQ. Okay, KEQ. Remember, this equation, products on top, reactants on bottom. So our product is going to be nitrogen trichloride. So the concentration of nitrogen trichloride goes on the top. And since there is a coefficient in the chemical equation, I do put that as an exponent in this equation. On the bottom, we put our reactants. We have two reactants. The first reactant is nitrogen gas. No exponent because the coefficient is 1. And then you multiply this by chlorine gas. And since the coefficient in the chemical equation is 3, there's going to be to the power of 3 for chlorine gas. All right? Now you start plugging things in. For our product, let's see, NCl3, 0.15 molar. And then this is going to be square. For our first reactant, nitrogen gas, the concentration is 0.25. And then we're going to multiply this by the second product, the concentration of chlorine gas, which is 1.50. And then we're going to cube this because there is a cube when you're writing the equation. Okay, now I'm going to show you simplified what the squared and cubed values are going to be. On the top, this simplifies to 0.0225. And on the bottom, we have 0.25 times 1.5 cubed is 3.375 if you type that in the calculator. Again, we're not going to write the units here because it's going to, the constants are pretty much unitless. So type all of this in the calculator. 0.0225 divided by 0.25 divided by 3.375. You are going to get approximately, so I'm going to turn this to a squiggly equal, approximately 0.027. And that's the constant value here. And since this number is smaller than 1, like it's a small decimal number, that means this equilibrium reaction actually favors the reactants. There's more reactants. And here's your practice problem. I encourage you to pause the video first before you take a look at my answers, but I'm going to show you the answer in 5 seconds. So I got my final answer to be about 50, and that means this equilibrium reaction favors the products a little bit more. There's just one practice for you to try after this. Go ahead and try it, and I'll give you some feedback.